Welcome to our discussion on hyperbolic functions. This is going to be just a lot of kind of memorization or things to put on a cheat sheet. There's not a lot going on with hyperbolic functions other than opportunities to take derivatives of other things and lists of kind of new functions to deal with. We've decided or we've discovered that certain even and odd combinations of the exponential function e to the x and e to the negative x come up quite often in mathematics and applications to other things, physics, econ, and things like that. And because they come up so often, we just gave them special names. And that's really where the hyperbolic functions came from. So most of this is just going to be recognizing things when you see them. These are the hyperbolic sine and cosine, and we name them after trigonometric functions because they have properties that are kind of similar to them. So here you go. Sine, hyperbolic sine, which some people call sinh. If you ever hear someone saying that, that's hyperbolic sine, is just e to the x minus e to the minus x all over 2. And then you can see that the hyperbolic cosine is the exact same thing but with a plus, right? And then the other four are defined normally. You know, tan is sine over cosine, cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent or cosine over sine, right? So they're all defined like the normal sine function. So really all that you need to quote unquote memorize here are the definitions of sinh and cosh, right? The hyperbolic sine and cosine. And it's pretty easy because it's e to the x and then an e to the negative x over 2, and it's just the sine, the bad thing, right, is minus, and cosine, the good thing, is plus. Okay, because these functions are kind of built similarly to these trig functions, you're going to get a lot of these similar identities. We see that the sine function, or the hyperbolic sine function, is an odd function, right? So when you take sine of negative x, it's negative sine x. The cosine function is an even function because cosine of negative x equals cosine of x. We get a very similar identity. Instead of cosine squared plus sine squared equals 1, it's cosine squared minus sine squared equals 1. And then we get corresponding ones with tangent and secant as well. Then we have kind of these double angle formulas similar to the other trig ones. Sine of x plus y equals all this stuff. Cosine of x plus y equals all that stuff. We can look at the proof of the standard identity of cosine squared minus sine squared equals 1. And the easiest way to prove these things is by subbing in the e's. So the e to the x plus the e to the minus x over 2, square it. You get something over 4, you square the other one, you get something over 4, you combine them because they're both over 4, all the stuff cancels, you end up getting 4 over 4, which is equal to 1, and ta-da, there it is. We can get the other one simply by, right, by the other one I mean the 1 minus tan squared equals secant squared. We can do that by just doing what we did normally with our normal trig identities, and that's divide the whole thing by a particular trig function, in this case cosh squared, right, the inverse cosine squared, and then that's how you get the second identity of the 1 minus inverse tan squared equals inverse secant squared. So like I said, a lot of this is just kind of memorization stuff that you would put on a list of derivatives, you know, a list of identities, just like anything else. The derivatives of these hyperbolic functions are pretty easy to compute because they're built on e, and we know that the derivative of e to the x is just e to the x. So taking the derivative of sine, of inverse sine, or sorry, hyperbolic sine, is just the derivative of e to the x minus e to the minus blah, 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 right? Well, you might think, oh God, I got to do the quotient rule. No, you don't. That's not a quotient, right? A quotient rule is a function over a function, and that is not what you have. You've got a function over a constant. That's really just 1/2 times e to the x minus e to the minus x. And you can take the derivative of each of those pieces, separately because they're just terms separated by pluses and minuses, so you don't even have to do the product rule. It's just a simple derivative of e to the x is e to the x, derivative of e to the negative x is e to the negative x times -1, and that's why all of a sudden the minus becomes a plus, and sinh becomes cosh, just similarly, right, almost identical to how derivative of sine equals cosine and the derivative of cosine equals minus sine. We now have derivative of hyperbolic sine equals hyperbolic cosine. Derivative of hyperbolic cosine equals hyperbolic sine. Aha, so there's the difference, right? It doesn't change signs. We don't get that -1 when we take the derivative of the cosh. Derivative of tan is still secant squared, just like before, right? Derivative of secant is secant tangent, only now it has that minus sign in front of it. So they're really all the same. They're just kind of messing with some pluses and minuses here and there. And then you've got the cosecant and cotangent ones as well. Just like our trig functions, we can use the chain rule, so we can now take derivatives of cosh of things other than x, right? In this case, the square root of x, and we know that the outer layer does the cosh to sinh, and then the inner layer, taking the derivative of that square root of x, gives us 1 over 2 square root of x, and that's how we get our final solution there. Now that we've discussed the hyperbolic functions in a relatively fast fashion, because there's really not much we can do with them other than just be aware of their existence and how to use them, we can then talk about how we can use their inverses. You know, these are functions, sine and tangent, and sinh and tan h, those two hyperbolics are both one-to-one functions, so they have inverse functions denoted by the inverse of each. And then the cosh function is not a one-to-one, but if you restrict the domain to just 0 and above, it becomes a one-to-one function, and then you can find its inverse as well. So just like any of our other functions, if they're not one-to-one, we do some domain restriction to make them one-to-one, and then we can come up with their inverses. Here are sketches of the three inverses. Here are the properties, right? Since the hyperbolic functions were all defined in terms of the exponential functions, it shouldn't be surprising that the inverses should be defined by the inverses of the exponential function, which is the natural log function. So the inverse sinh function, the inverse hyperbolic sine function is defined in terms of a natural log, and so is the inverse cosh, and so on and so forth. They're all going to be defined in terms of natural logs, which means taking their derivative is also fairly easy, right? Because the derivative of a natural log of some stuff is just the derivative of the stuff over the stuff. Okay, we can prove that the inverse hyperbolic sine is equal to the natural log of those things by starting with y, equaling it. So then we know x equals sine of y. Right, we're kind of just doing the inverse of the inverse, which means we can now define it in terms of e's, and then we can kind of multiply by 2, right, to multiply both sides by 2 so that we have 2x equals these e things, and then move the e's over and now set the whole thing equal to 0. If we multiply everything through by e to the y, we get e to the y times e to the y, which is really e to the y squared, minus 2x e to the y minus 1 still equals 0. You'll notice this is now a quadratic, right? This is an e to the y piece, an e to the y squared piece. So it's a quadratic in form. Those are those types of things you guys really need to keep an eye open for. They come up a lot in calculus and in other things. Seeing something that is quadratic in form. By using the quadratic formula, we can solve for what e to the y is. And we get this. And you'll note that because e to the y has to be greater than 0, because if you know what the e function looks like, right, the e function is very simply, if you don't remember, looks like that, right? So e to the y is always greater than 0. There's really no difference between e to the y and e to the x. It's now just in terms of y instead of x's, right? So because of that, we know that this piece is no good, because this is slightly bigger than x, right? X squared plus 1, and then when you take the square root, it's going to be slightly bigger than x. So when you subtract it from x, that's going to be a negative number, and that's no good. That means that the plus and minus sign just becomes a plus sign because the minus part is inadmissible. It's algebraically true, but it's not true in the context of the question. Therefore, to solve for y, now you just take the natural log of both sides, and that's where you finally get the answer. Here are the derivatives of the hyperbolic functions. This really just comes from taking the derivatives of the natural log of the stuff and then cleaning it up algebraically, and you get these things. And you might be thinking, well, really, why do I care about these things? Well, you really don't right now, but when you move on to Calc 2 and you have to be taking antiderivatives, right, integrals of things, when you come across an integral of something of this form, you know that its answer is going to be an inverse hyperbolic sine function. So it just gives you some more forms of things to be looking for that you can anti-differentiate back to something else. And that's really where these are going to come into play, at least in the calculus realm, the most for you guys, other than just, practicing. Alright, so just remember that the inverse hyperbolic functions are all differentiable because the hyperbolic functions are all differentiable, and these are just inverses of them. Right? So any function that's differentiable, its inverse will also be differentiable. We can prove that by going through the motions, taking the derivatives. Right? If we want to let y equal the inverse sine, then we know inverse sinh, then we know sinh of y equals x if we differentiate this equation implicitly with respect to x, because we're taking ddx of it. So you take the derivative of hyperbolic sine, which gives you hyperbolic cosine, and then times the derivative of the inside, and the derivative of the inside is the derivative of y, which is dy dx. And then that's going to be equal to the derivative of x, right, which is just 1. So now solving for dy dx, it's just going to be 1 over cosh of y. Well, since cosh squared y minus sinh squared y equals 1, and cosh of y is greater than or equal to 0, we know that cosh of y equals all of this stuff. So when we have 1 over the hyperbolic cosine of y, by substitution we have 1 over all of this stuff. And from the very beginning, this sinh of y was x, right? If you don't remember, go back up here, right? Sinh of y equals x. So by substitution, sinh squared of y is just x squared, and ta-da, there it is. Okay, now remember this came from the fact that if y equals the inverse hyperbolic sine of 8x, then the hyperbolic sine of y equals x. Just the idea of, what does it mean to be an inverse? Okay, and that's pretty much all the bits and pieces you need to worry about with these hyperbolic functions. It's really just going to be practicing with their definitions, right? The definitions of their derivatives, basically, their identities, their inverses. It's just going to be some more stuff to add to the list of things that you can take derivatives of and identities you can use to kind of clean things up.